Okay, in this video, I will talk about EMF, electromotive force, right? Why EMF? Because this is one of the most common questions that are asked in the trials also. So you can find EMF question in the Malacca paper, in Kedah paper, in the Selangor paper, MRSM paper, Putrajaya paper, okay? So very, very common, right? So we think this might be one of the topics they will focus on in your SPM. So EMF, right? Okay, stands for electromotive force. Okay, and electromotive force, usually there will be a symbol of E like this. Okay, but sometimes we might accidentally use capital letter E lah. Okay, but usually capital letter E is used for energy. Okay, what is this electromotive force? Electromotive force is actually similar to potential difference or voltage. So if you think about it, right, voltage is basically how much energy you need to push the charge from here to here. Okay, how much energy you need or how much work done to push the charge from here to here. So when I say the voltage across here is 3 volts, the voltage across this resistor is 3 volts. That means that I need 3 joules of energy to push one charge from here to here. Okay, but EMF, right, is the total voltage, we can say, the total potential difference, or the potential difference, the voltage of the electric source, the voltage of the battery, right? So that means if let's say I say my battery is 9 volts, the EMF is 9 volts. It means that the battery will give 9 energy to push one charge, go one whole round. Okay, yeah, to push a charge to go one whole round. So that is a total voltage, the total EMF. Okay, so when we say EMF, it will always relate to another thing, which is internal resistance. Okay, internal resistance. So internal resistance, right, usually use the letter, small letter R. Because big normal resistance, we use capital letter R. So internal resistance, we use small letter R. Internal resistance is this super small resistance that is inside the battery. Okay, so like when you want to go from one end of the battery to the other end, you will have to go through some resistance. It's not perfect one. So that small amount of resistance is called internal resistance. That's why we use small letter R lah. Okay, so then there will be a formula, right? The formula is this: E is equals to V plus IR. Okay, let me explain how to get this formula. Now, the E is the total voltage of the battery. Okay, usually I would like to say voltage is like how much money you have, how much money you bring, how much money you spend. Okay, so if let's say you have 9 volts of EMF, 9 volts of the battery, that means that every time you come out, right, you will spend, you will bring 9 volts. You'll bring 9 ringgit, $9. Okay, so when you come over here, you will need to spend your money, right? Now, how much you spend depends on whether got other resistor and how big is the resistor and all that stuff lah. Okay, but let's say it's just one resistor only. This one single resistor, you are supposed to spend 9 volts. You're supposed to spend 9 ringgit. Because, right, Mama say, cannot come home with money. Mama say you must spend all your money, only you can come back home. Okay, so I'm forced to spend all my 9 ringgit here. Okay, supposedly lah. So the voltage here, right, the potential difference here should be 9 man. But when I do experiment, this voltmeter doesn't give me 9. This voltmeter gives me 8.6 volts. Okay, then where did the 40 cent go? Where did the 0.4 volts go? It's because before you even come out from your house, right, you have to pay your mama already. Okay, your mama say you want to go out, pay first. Okay, so this 9 ringgit that you have from your house, you need to pay your mama 0.4 volts first. Then only the rest you bring up. So you spend 8.6. Okay, so you see, your total money, right? total EMF is equals to the amount that you can spend outside. This voltage is the amount that you can spend outside plus okay, a small voltage that you have to pay at home. Small voltage, small potential difference you need to pay your mama. Okay, so this small voltage can be calculated using, we know that what? V is equals to IR ma? This one you should know one. Always remember, this is one of the most important equation. V equals to IR. So this V, I can write it as IR, but small r, because the resistance here is very, very tiny. This resistance is big one. So this V is big I, big R. But here, small r. Why the I no need to small? Because I is the same. The current here and the current here exactly the same. Okay, but the resistance here very small, so like that. That's how you get the formula. And if you want to break down this one even more, can also. Big I, big R plus IR. Okay, then you can even write it like this. You take the I out, you can even write it like this. That's another way. Depends lah. If they never give you the V or anything, they just give you the R, right, and the I, then you can use this way lah. Okay. Now, one last thing is that sometimes you might need to convert this into graph form. Okay. So this way, right, they will give you a graph. Okay, they will give you a graph, and the graph will be like voltage versus current. Okay, and then it will be a straight line, right? It will be a straight line. Okay, so any straight line graph, you can always write it as y equals to mx plus c. This means the y-axis is what? This is the gradient. This is x-axis is what? This is the y-intercept. So this y-axis, right, is v. I need to find a way to move this v until it stay here. Okay, let me remove all this first. Right, I need to find a way to move the v to stay here. And then this x-axis is what? I need to find a way to move this I to stay here. Okay, so what can I do? Number one, I can move the IR to the other side. Okay, I move the IR to the other side, then it becomes EMF minus IR equals to V. Okay, I can write V equals to EMF minus IR lah. Okay, understand right? So now V is in the correct position already. Okay, V stay here already, correct. Okay, but I still not in the correct position yet. So what can I do? I can move, because EMF minus IR is the same as writing negative IR plus EMF. It's the same. Okay? Yeah, negative IR plus EMF. Then I times R can write as R times I, same or not? Yeah, A times B equals to B times A, same, right? So I write this as negative RI plus EMF. So y-axis locked already, correct position. X-axis locked already. So everything else also must be locked. So if they ask you what is the EMF, you find what is the y-intercept. Whatever this number is, this is the EMF. Okay? If they ask you what is the internal resistance, right? You just need to find negative M. Okay? Find the gradient, y2 minus y1 over x2 minus x1, and then negative it. Why? Because, you see, negative R is M. So R is negative M. So you will still get back a positive number one. You will get back a positive number. Because this gradient is going to be negative, then the negative will become positive. Okay? So basically, this is the basics of EMF and internal resistance. Okay? Then next, we will look at some of the questions from the trials. Okay, so this is a Malacca paper, right? Malacca trial paper. question number 4. Okay, paper 2 lah, of course, right? Question number 4. So here we have an electric circuit to do an experiment to determine electromotive force and internal resistance of the dry cell. Okay, so this graph is a graph of potential difference, voltage over current, okay, against current amperes from this experiment. Number 1, what is the meaning of electromotive force? So like just now I said, electromotive force is how much energy to push one charge to go in a round, okay, to go around the whole circuit, right? So you can say the energy required, the energy required, or you can say the work done, right? Both are the same, work done and energy. Okay, the energy required or the work done to move 1 coulomb, okay, 1 coulomb of charge around a complete circuit. Okay, the energy required or the work done to move 1 coulomb of charge around a complete circuit. Yeah. Okay, next, tick the correct answer in the box provided. Where is the suitable position of a voltmeter? Okay, so the voltmeter, right? Okay, so we have a resistor here. We have this is a variable resistor. Okay, we have an ammeter here, and then we have another spot here, one spot here, one spot here. So voltmeter must be connected in parallel. Okay, must be connected in parallel. So either X or Y only. Okay, cannot be A. A is definitely ammeter lah, right? So if you want to measure the resistance and the potential difference of the resistor, of course you put it here across the resistor. But right now we are trying to measure what? We're trying to measure the resistance of the battery of the dry cell. Yeah, it says here, determine the resistance of the dry cell. So we must put it across the battery law. So it's going to be X. Okay, next. Based on the diagram 4.2, determine the electromotive force of the dry cell. Show on the graph how you determine the electromotive force of the dry cell, right? So here is back to what we discussed just now, okay? So I just start from scratch. I look at the formula sheet, okay? You can find this in the formula sheet, okay? Under electricity, you see the electromotive force. This is the formula, okay? EMF is equals to V plus IR. And then I go back. Okay, so I write it down. Electromotive force EMF equals to V plus IR. Okay, then I have a graph, which means I must try to feed it into Y equals to mx plus C. So how to feed it there? First of all, I keep V on one side. Everything else I move to the other side. Okay, so I'm gonna get V is equals to EMF minus IR. Okay, because I moved this over here. And then negative IR, bring to the front, E bring to the back. So negative IR plus EMF. Lastly, the I and R can switch position. So V is equals to negative RI plus EMF. Okay, if I want to find the EMF, right? Everything is fixed already. If I want to find the EMF, I need to find the y-intercept. The C is the y-intercept. So here I have to draw a line. You take your ruler, you draw a line, extend. Okay, then you mark. Okay, this is the y-intercept, 11. Okay, so that's your answer, 11 volts. Okay, 1 mark for the answer, another mark to show in the graph, this thing. Okay, because the question already says show in the graph, right? And then what is the internal resistance? So the internal resistance here, negative internal resistance, this small r, is equals to the M. Let me calculate the M first, right? So the M is the gradient. y2 minus y1 over x2 minus x1. Okay, so I choose 2 points. Let's say I choose where is a good point? 8 is not 2, right? 8, okay lah, never mind lah. Let's just discuss this is 3 ma. Right. So this is 8, 3. This is 0, 11. Okay, right? But if you want to be safe, you don't use the point that you draw. You use the one that he draw. He drew it here just now until here. So this is 2, 9 also can use. Okay, so y2 minus y1, whichever way you want to do, this minus this, or 3 minus 9 also can. So 9 minus 3, divide by, and then x2 minus x1, 2 minus 8. Okay, so this is 6 over negative 6, which is negative 1. And remember, from here, okay, from here, negative r is equals to 1, because negative r is equals to m. So negative r is equals to negative 1. Yeah, m is negative 1. So r is equals to 1 ohm. Okay, r is equals to 1 ohm. All right, next one. Which of the light bulbs, right, will be brighter? Okay, I have 2 kinds of arrangement. I have arrangement in series, and then this one is arrangement in parallel. Okay, so which one will light up brighter? This one, if you've done enough questions, right, actually you should know one. Okay, it's always the parallel that light up brighter. So you say circuit arrangement 4.3b light up brighter. Okay, why? Because in the parallel arrangement, you always have lower effective resistance. Okay, when anything with resistance arranged in parallel, the total resistance will be lesser. Okay, that's the law, right? So you can say the effective means like total, the effective, not just resistance, but internal resistance. The effective internal resistance is lower in parallel arrangement. Okay, lower effective resistance in parallel arrangement. Then when there's lower resistance, you get more current flow. Okay, so you say greater current, okay, greater current flow in the circuit. Okay, yeah, circuit arrangement 4.3b light up brighter. The effective internal resistance is lower in parallel arrangement. Greater current flow in the circuit. Okay, right? So of course you can pause this video anytime if you cannot copy, or just go back if you miss out any of the parts. Okay, then we can look at the next question. Okay, so this is the Kedah paper. Yeah, Kedah paper 2, question number 6. Okay. So diagram 6a and 6b shows 2 circuits consist of identical dry cells, means the same batteries, okay, in parallel arrangement, both also in parallel arrangement, but with different number of dry cells. This one got 2, this one got 3. The voltmeter reading when switched off are 1.5 volts, meaning when the thing is not fully connected okay, when current is not flowing, the voltmeter reading is 1.5 volts. Each dry cell has the same internal resistance. Okay, so question number 1 is the same question as we did just now. What is the meaning of electromotive force? So again, electromotive force is the energy required or the work done to move 1 coulomb, okay? 1 coulomb of charge, okay? Around a circuit or in a complete circuit. Around a complete circuit, okay? How much energy you need to push the charge 1 whole round. Okay, what will happen to the voltmeter reading in both circuits when the switch is on? Okay, now one thing to remember about this EMF problem, okay, is that whenever the switch is off, okay, whenever the switch is not fully connected, right, open like this, the voltmeter will always tell you the EMF. But once the switch is connected, the voltmeter will actually tell you the voltage of this thing. Yeah. Remember inside our equation, we got 2 things, right? We said the EMF is equals to the voltage plus IR, okay? Or like the big voltage plus the small voltage here. Okay, so EMF is the total, yeah, total. This one is the voltage or the potential difference of whatever object is outside. Okay, and then this is the potential difference through the battery. So every time it's open, right, you always get the EMF, which is the maximum amount. You cannot be more than the EMF, right? And then once you connect it, then only it becomes smaller. Okay, because this voltage is definitely smaller than the EMF. EMF is the max already. Okay, so when it's open, you get EMF, which is the maximum. When you close, then you will get lesser. So the voltmeter reading will decrease. Okay, you can say the voltmeter reading decreases. Okay, next. Based on the diagram, compare the EMF in both circuits. So the EMF here and the EMF here, okay, what is the difference, right? So you see the voltmeter reading in both circuits when off, which means EMF is 1.5. This also 1.5, this also 1.5. So the EMF for both is actually the same. So you say diagram 6A is equal to diagram 6B. Okay, diagram 6A is equal to diagram 6B because both also have EMF of 1.5. What is the effective internal resistance in both circuits? Effective internal resistance means the total internal resistance. And the thing about parallel is that the more things you connect in parallel, the lesser your total resistance, the lesser your effective resistance, okay? Because you are opening more roads for the current to travel. So the current will actually travel better, okay? So this one will have lesser resistance than this, okay? Or this one got more resistance, whichever way, right, also can. So you can say diagram 6A greater than diagram 6B. Okay, diagram 6A greater than diagram 6B for the internal resistance. Okay, then what about the brightness of the bulb? The brightness, you just have to look at the picture lah. Okay, you see this one got lesser dots here, this one got more dots. So you can say diagram 6B brighter. Okay, brighter than diagram 6A. Okay, B is brighter than A. Yeah. Right? Then the next one, based on the answer, state the relationship between effective internal resistance with brightness. So what's the relationship between effective internal resistance and brightness? You see, this A got more effective internal resistance, right? But then 6A, lesser brightness. Okay, lesser brightness. So the more internal resistance you have, the lesser the brightness. Or you can write the other way around. The lesser internal resistance you have, the brighter you are. Okay, so you say the smaller or the lesser the effective internal resistance, the smaller the effective internal resistance, the brighter the bulb. Okay, the smaller the effective internal resistance, the brighter the bulb. Yeah. And what is the relationship between the effective internal resistance with the current flow? Okay, so current flow and the resistance, of course, will be the other way around also lah. More resistance, lesser current flow. Less resistance, more current flow. That's the whole meaning of resistance, man. Okay, so you say the, yeah, use back the same as the top lah. The smaller the effective internal resistance, the greater the current flow. Okay, the greater the current flow. Yeah. Okay. Next, internal resistance of each dry cell is 0.5 ohms. Calculate the effective internal resistance of each circuit. So now you have to calculate what is the total resistance, what is the effective resistance. Okay, so if you do this 6A, right, there's 2 ma, each of them is 0.5 ma. Okay, in parallel, the way to calculate is this. Okay, so let's say diagram 6A first. Okay, in parallel, your formula is this: 1 over R. I use small letter because internal resistance is small one. 1 over R is equals to 1 over R1, which is 0.5, plus 1 over R2, which is 0.5. Okay, so this is equals to 2 over 0.5. Okay, so R is equals to, how to get, because this one is 1 over R. You cannot just calculate this, then you just say, oh, done. No, you must flip it around because I want R. I don't want 1 over R. So R is 0.5 divided by 2. Okay, 0.5 divided by 2 is 0.25 ohms. Okay, for diagram 6B, it is 1 over R, because you got 3 now, 1 over R equals to 1 over 0.5 plus 1 over 0.5 plus 1 over 0.5. 1 over R is equals to 3 over 0.5. So R is equals to, again, just flip the number around, 0.5 divided by 3, which is 0.16. 1666667, right? Okay, so 167, yeah, and it is lesser than the two cells one, okay, which is correct. Yeah, it should be lesser. Okay, so this is how to calculate the effective internal resistance, right?
Okay, so this is the Putrajaya paper, right? Putrajaya paper 2, set 1, 2022, question number 6. We have a 6.1, we have an electrical circuit, consists of 6 similar dry cells, means 6 same battery. and each of them has an EMF of 1.5 volts. So when you connect them in series, right, their voltage or their EMF will add up together to become 9 volts. Okay, 1.5 times 6, 9 volts. Each of them has an internal resistance of 0.5 ohms. Diagram 6.2 here is another electrical circuit, and this one has one dry cell, okay, that is 9 volts, okay, and the dry cell has an internal resistance of 0.01 ohms. So question number 1, what is the meaning of electromotive force? See, you cannot run away from this question. So I'm not going to write this question anymore because previously we have done this many times already. Okay, so based on diagram 6.1 and 6.2, compare the brightness of the bulb. So if you look at the brightness, again, just look at the picture. This one got longer lines, this one got shorter lines. So 6.2 is brighter than 6.1. Okay, diagram 6.2, brighter than diagram 6.1. Okay, next, compare the total EMF in the circuit. So the total EMF here is 9 volts, and the total EMF here is 9 volts, written for you already. Very good, they write for you. If they never write for you, you need to know this one 1.5, 1.5, 1.5, all add together is 9. Okay, so both have the same. You can say diagram 6.1 equals to diagram 6.2. Okay, next, compare the total internal resistance in the circuit. This one also use your eyes only. The total internal resistance 6.1, 0.5 ohms. The total internal resistance in 6.2, 0.01 ohms. So you say diagram 6.1 greater internal resistance than diagram 6.2. Okay, and lastly, compare the magnitude of the current flow. So how to compare the magnitude of the current flow? Here they give you ammeter already. Ammeter is to measure current. So we assume ammeter always starts 0 from the left, and then 1, 2, 3, 4, 5 like that go to the right. So you see this is a low reading, this is a high reading. Okay, if not, then you will have to compare based on the brightness already. Okay, brighter bulb usually higher current lah. Okay, lesser resistance usually higher current lah. Okay, so you can say diagram 6.2 greater than diagram 6.1. Okay, then after compare, naturally you will have to state the relationship. Okay, so the relationship between brightness of the bulb and total internal resistance. So you can see, right, this one 6.1 more total internal resistance, but lesser brightness. Okay, lesser brightness. So, okay, for this, right, you have to be careful because you have to think about which thing affects which one. Okay, you see the way they write, brightness of bulb and total internal resistance. Some students will say, oh, the brighter the bulb, the lesser the total internal resistance. No, it's the total internal resistance that affect the brightness. So you have to say the lesser or the lower the total internal resistance, the brighter the bulb. Understand? You have to show them you know which thing affects which one. Okay, and in this case, it's the resistance that affects the brightness. Yeah, and then here same also lah. The relationship between total internal resistance and the number of dry cell. You think the internal resistance affect the number of battery, or the number of battery affect the total internal resistance? Of course, it's the battery affect the resistance, correct or not? So you say the greater the number of dry cells. The greater the number of dry cells. See, more dry cells means what? More dry cells means more resistance. One dry cell, lesser resistance. Okay? Yeah. So the greater the number of dry cells, the greater the total internal resistance. Oops. Internal resistance. Okay. Last question. A car is turned on with an electric current from a lead acid accumulator with an electromotive force EMF of 12 volts. If the accumulator is replaced with 8 dry cells of 1.5 volts each, can the car be turned on? Give one reason for your answer. So 2 marks are, first mark is answer, can it be turned on or not? Second mark is give the reason. So you see, this car need 12 volts to start. Okay? Usually, the lead acid accumulator, which is the car battery, give him 12 volts. When I replace with 8 dry cells of 1.5, although 1.5 times 8 is what? 1.5 times 8 is also 12, okay? But because now you use 8 batteries, then the internal resistance will be much bigger already. So actually the car cannot turn on. Okay, so you say the car cannot turn on. Okay, why? Because the total internal resistance is high. Okay, the car cannot turn on because the total internal resistance is high. All right, the final question we will look at is Selangor paper. Okay, Selangor paper set 1, right? Paper 2, question number 10. So here we have an electric circuit to determine the EMF and the internal resistance of the dry cell. Very simple circuit if you want to find EMF and internal resistance. You just need a battery, the dry cell. You connect a voltmeter across it. Okay, you have an ammeter. You have a variable resistor or a rheostat, means you can change the resistance. Okay, then you have a switch, right? So what is meant by EMF? We will skip the question because you should know the answer already. Okay, with the aid of a graph, they already tell you they want the graph. So how to find the EMF and the internal resistance of the dry cell? So our graph look like this one. Okay, the shape of the graph will be VI, and remember, the line is coming down. Okay, the line is coming down, right? Whether you touch the x-axis or not doesn't matter, but you must touch the y-axis, okay? Because the y-intercept is a very important number, right? So from here, because we know that y is equals to mx plus c, and we know that EMF is equals to V plus IR. Okay, from the formula sheet in front. Then you arrange. I already arranged many times. So if you arrange it right, you will be able to get V equals to negative RI plus EMF. Okay, yeah, if you arrange it. So then you can tell them, right? You can tell them the EMF is the y-intercept. Okay, the EMF is the y-intercept. And then the internal resistance, okay, the internal resistance is negative gradient. Okay, is negative of the gradient. Understand? Yeah, because okay, the EMF one you should know lah, right? EMF is C which is a y-intercept but the R, because remember, gradient is equals to negative R. So R is equals to negative gradient. Understand? So the internal resistance is negative gradient. That's how you do this question. Okay? So now we have an essay question. We need to choose a car battery that can supply very high current, okay, to the motor of the car, and also activate other parts of the car. Sorry, and also activate other parts of the car. So first is the internal resistance. If you want very high current, you must have low internal resistance lah. Okay, low internal resistance. Okay, so I don't have a space for me to write. Okay, usually you write it in your test pad, but low internal resistance means higher current. Okay, next is the type of battery. Now, the type of battery, right? There's wet battery and dry battery. Wet battery means got liquid inside. Okay, so if you want to have a battery, right, and you want to move it around or everything, okay, because the car you need to change battery on, right? Then you will always choose dry battery, because everything dry is always easier to handle. Wet is very hard to handle. It will spill, right? It is actually heavier, okay? So we can say the dry battery is easier to handle. Okay. The cells. Should we arrange it in series or parallel? Okay, by now, if you see two hit like that already, right? Okay, then you will know the next answer will be these two already lah, right? Okay, so why do we want the cell to run in series? Okay, because the series will give a higher voltage. Okay, the series will give a higher voltage. Although you always say parallel will have lesser resistance, but since we already choose a lower internal resistance one, we can put them in series one. Okay, no problem. Yeah, and since you already know the answer forced you to choose this, then you must explain it to them. Okay, series will have higher voltage, because in a series, all the voltage add up together one. Okay, and last one is the rate of oxidation. Rate of oxidation means what? Rusting, right? So lower rate of oxidation means does not rust easily. Okay, does not rust easily. So this one, 1 mark, 2 mark, 3 mark, 4 mark, 5 mark, 6 mark, 7 mark, 8 marks. The last 2 marks is your choice will be X, because X has a lower internal resistance. It uses dry battery. It has a series arrangement of cells, and it has a low rate of oxidation. 10 marks. Okay. Now, the last question, they give you the dry cell with an EMF of 1.5 volts. What is the internal resistance of the dry cell? Oh, they say, sorry, when the switch is closed, the reading of the voltmeter and ammeter are 1.2 and 0.3. Okay, so I said this in the previous question. When the switch is open, no electricity flow. The number here is EMF. Okay, 1.5. When you connect the switch and electricity flow, the number here becomes V, potential difference. Okay, potential difference across here, right? So we can just straight away use our formula, EMF equals to V plus IR, because we know the EMF is 1.5, and we know the potential difference V is 1.2. Okay, here. This is after you close, it becomes V. When it's open, it's EMF. Okay, plus I is 0.3, also in the question, times R. Okay, so you bring over, become minus, so 0.3 equals to 0.3 R. R is equals to 1 ohm. Okay. All right. Now, find the value of this R. Okay, find the value of this R. So the V is the potential difference across here. meaning how much money you can spend across this. Okay, how much money you can spend across here. Understand? The total V here is 1.2. The current here is 0.3. If I have the V, I have the I, can I get the total resistance? I can, okay? Because I know that V is equals to IR. Okay, we are not using EMF because EMF means you haven't paid inside. After you pay inside, you're only left with 1.2 volts. Okay, so 1.2 volts equals to 0.3 amperes times the total R, total R, not to be confused with the answer they want. Total R. So R total is 4 ohms. Okay, 4 ohms. Now, how do you calculate the total resistance here? You see, these two are in parallel, right? So parallel means it will be 1 over R equals to 1 over 2 plus 1 over R. Okay, all right, I should. Why do they use R here? Okay, I'm going to make this R1 so it's not so confusing. Okay, R1 like that. So 1 over R, which is the total resistance here, equals to 1 over 2 plus 1 over R. Okay, so then you can say this 1 over R is equals to, so let's say I multiply with R1. Wait let me think first. Yeah, okay. So this one I multiply with R1, this one I multiply with 2. I just want to make the denominator the same. 2R1. Right. Over, this is R1 plus 2. Okay. All right. I split it up first. Like that. This one multiply by R1, you get R1 over 2 R1 plus this one multiplied by 2, you get 2 over 2R1. So 1 over R is equals to R1 plus 2, because the denominator is the same. You can put them together. Okay, so this R is equals to 2R1 over R1 plus 2. Then this thing is here only. You still need to plus the 3. Okay, so the total resistance is equals to this 3 plus this whole thing, which is this. Okay, 3 plus 2R1 over R1 plus 2. The total resistance we know already, right? The total resistance is 4. If you bring this over minus, 1 is equals to 2R1 over R1 plus 2. Okay, this whole underneath, I bring there become times 1 times 1. So R1 plus 2 times 1 means the same thing, equals to 2R1. Okay, you bring this one over here, minus off, then you get R1 equals to 2 ohms. That's your answer. Okay, if you couldn't get any of this right, you just go back a few seconds, go back a few minutes, and then you try to watch it again. Okay, if you really still don't understand, then you come and find me. Yeah, so hopefully this video will help you with the EMF topics. Okay, because seems like there's a high chance EMF will come out right? So if you have any questions, you know where to find me Okay.